Okay. We are going to look today about how to solve simultaneous equations using matrices, which we've already touched on. You won't find that difficult or new, but we're looking at more particularly at the geometrical interpretation of that. I'm sorry. There we go. So I think if you need it, this is in your content library. There we are. Okay. So the equation ax plus by plus cz plus d is the equation of a plane. So if you had three equations of that form and solved them simultaneously, geometrically, what are you finding? Finding the intersection of three planes. Now, if you think about three planes in space, there are, I reckon, 5 possible distinct configurations where they could be laid out. So, Ella, can you give me one example of the way you might have three planes in space?
They're all parallel.
They're parallel, so they might all be parallel. No intersections. In other words, no two of those, all three of those equations can't be true at the same time. We can say equations are inconsistent. Okay, Robert, can you give me another configuration? Okay, good. So two parallel. Another intersects both. But again, it's true to say there are no points of intersection of those three planes. Yeah. So again, no intersections. I've got a diagram to show these. They're inconsistent again. Okay. Andy, what about another configuration? At one point. Yeah, okay. Give you one intersection. Okay, two more configurations. There's we've got all parallel, got two parallel. Yeah. Okay, so they all intersect in a common line. That's known as a sheath. How many solutions do you have to that? So I said no intersections. I should have said no solutions. It doesn't matter. I'm not wrong what I've written, but I'd rather say no solutions. No solutions. How many solutions are there in that one bed? Infinite number of solutions. And anyone for the fifth one?
When they're like a triangle, so
yeah, good, exactly right. Yeah, except it's three-dimensional, so a triangular prism. Yeah, very good. Again, no solutions. Okay, I think I've got ready a picture to show, just in case you have trouble visualizing it. Somewhere in here. There it is. It's from the textbook. Okay, and that's what they look like. There's the triangular prism, there's the sheath intersecting at a single point, 3 parallel, 2 parallel. So, okay, now one of the earliest uses of matrices, and I think actually the early use, I'm not sure about this, I should look it up, I like the history of these things. I think matrices were developed as a way of solving simultaneous equations, though Dr. Marcus and I wanted to teach you them as transformations because we think that's the hardest thing to get your head around. I think actually solving simultaneous equations is where they were first used before they became a more abstract concept. So you can write any equation, any system of linear equations in matrix form, and it just means you're writing less, doesn't it? We can write that as what you can actually imagine, because I think it's true, is that the rule for matrix multiplication was originally developed to be as it is, simply so you could say that. So if we write that down as a shorthand notation for that equation on the left, the matrix. Yeah.
There is a mistake in your equations. You have x plus 3y minus 2x.
X plus 3y minus 2. Oh, I see what you mean. Thank you. Thank you. Yeah, 2z, that should be. Okay, so we're using the matrix just to represent the coefficients, and then for it to work, you can invent the rule of multiplication of matrices, and that's what you get. Okay, so how would we solve that? Well, we would solve it by multiplying both sides, pre-multiplying both sides, and it is really important it's pre-multiplying, by the inverse of the matrix. Which we're not going to do yet. You're going to do it in a second, but I want to look at what it, if we try and calculate the inverse of the matrix, so that should say -1 there. I want to look at what it means if the matrix is non-singular. Now I'm going to ask Robert, because we struggled with singular yesterday, didn't we, Robert? So hopefully now you know. If the matrix is non-singular, then what does it mean? Yeah, so what does it mean in terms of the geometric? Does it tell you, if the matrix is non-singular, does it tell you which one, what the configuration of the planes is? What do you think? Yeah. It means you'll get solutions. So they intersect at a point.
And also be aligned there as well.
But that would give you an infinite number of solutions.
So how would you tell if it?
Oh, well, that's what we'll come to. I always get nervous. Because by saying there are solutions to that, it means I can find, if you know what the inverse is, you're going to get a value for x and a value for y and a value. Yes, I'm confident now. You made me doubt myself. You are going to get a value for x and a value for y and a value for z, aren't you, if you've got the inverse of the matrix, which means you found a point. There is one solution. Intersect the point. the matrix is invertible, if it has a determinant that's not equal to 0, then they do intersect at a point. Otherwise, the determinant being 0, you might have 3 parallel, 2 parallel, sheaf, prism. Okay, and you've got to be able to work out which one it is, and that's where it gets a little bit fiddly. Okay, but the basic idea is if you find you can tell whether they're parallel, whether they're 3 parallel ones or 2 parallel ones, just by looking at the rows of the matrix, aren't they? If one row is a multiple of another, they're parallel. The determinant is 0, and we already know actually, or maybe we already said that if one row was the same as another, the determinant will be 0. It also follows that if one row is a multiple of another, the determinant will be 0. Okay, so if we look at the matrix and they're not got one row being a multiple of another, they're not parallel, so it's either a sheaf or a prism. So what's the difference? And the determinant for both will be 0. What's the difference between it being a sheaf or a prism?
There's a prism. There's like 2 equations. Each of the equations has solutions with one other, but not together.
Okay, all right. What we'll say, I mean, that's true. If it's a sheaf, they're not parallel, but they are consistent. We'll see what we mean by consistent. And prism, there's not parallel, but they're inconsistent. Now, a very simple example of inconsistent would be if you had 1, 3 minus 2 equals 5, and 1, 3 minus 2 equals 7. Yeah, they would be inconsistent solutions if you inconsistent equations. But normally it won't be that easy. It's as you solve it, you find effectively what it means is one of the rows is a combination of the other rows. Like if you multiply this row by something and add it to a multiple of this row and get this row, that means that row depends on those 2 rows, as it were. And if they gave different numbers, then they would be inconsistent. It's going to be much easier when you actually try and do it. So that's the basic idea. We'll just find out with the first one. I want to know, first we'll solve the first one. So it's going to be just, and then I just need to, so you solve that, and I just need to check what the question is. Do I want to ask, are they, what value of k?
Sir,
Yes.
can we use our calculators?
Yes, you can. Yeah, as long as you are now confident in finding the inverse of a matrix by hand, I'm happy for you to use your calculators to find the inverse. Yeah.
If you get a math error on your calculator, does that mean it doesn't have an inverse? Or I typed something?
Oh, are you telling me that's what happens?
Like when I typed in the matrix.
Oh, I feel like I've recopied down the question wrong because I've looked at this somewhere. Hang on. Might be wrong.
Maybe I typed something.
No, it's quite possible. The question, I just ripped it out of the book because it had a nice follow-up, which I forgot to. So what you're all finding, it's oh, okay. Oh no, it is. It is. Sorry, that is true. It's right. So it's investigate with 10 and 12. Okay. I want to know about the configurations. What do I want to know? The configurations with these two. So you know that they don't intersect at a point, whatever the value of k, they don't intersect at a point. Okay, so you know it's one of those four options. Another one you can rule out. So I want to know basically, are we talking 3 parallel, 2 parallel, sheaf or prism for each of those two values of k?
Sir,
Yeah,
my calculator tells me it has no inverse.
that's right. So what does that mean?
It's a singular matrix.
Yeah. So geometrically, it means, doesn't it, that they don't intersect at a point. So these three planes don't intersect at a point. So what I want you to do now, the bit I just put up there, is I want you to tell me what their configuration is when k is 10 and what the configuration is when k is 12. Are they parallel, are they a sheaf, or are they a prism?
Okay, thank you,
Yeah.
sir.
You found
No,
that
I'm not quite sure.
Sorry?
I'm not quite sure why if it's not on singular and there's only one solution. I can't quite see that.
You can't quite see what?
I can't quite understand what you mean by if it's not singular then there's one solution.
Well, what does singular mean?
Singular means that when it's sort of like a line, isn't it? When the determinant
Yeah,
equals
but
zero.
it's when the determinant is 0. So if the determinant is 0, you can't find an inverse. So if you can't find an inverse, you can't solve the equation. So if the determinant is 0, it means they don't have a unique solution. They don't intersect at a point. What we were just talking. So if the determinant is 0, it must be one of these four cases.
Yep, I get it.
So they don't intersect at a point, but there could be 3 parallel, 2 parallel, a sheaf, or a prism.
Sir.
Yeah.
Sorry, I can't quite see why, like when two planes are parallel, why do they make the matrix, singular?
You weren't here at the start, were you? So
Yeah.
yeah.
So the determinant it's 0, right?
The determinant is 0, which means they don't intersect at a point. If the determinant is 0, it means you can't find a solution. You can't find an inverse of the matrix, which means you can't find a solution. If you can't find a solution, we discussed there were 4 possible configurations of the planes, which are those detailed there, and there's pictures of them.
So you can't actually comprehend it with like a 2x2 matrix, like because the singular matrix in 2x2 it just smashes everything onto a line.
Yes, in 3x3. Yeah, so we're thinking of it in terms of, in 3x3 it's the same. If you think of it transformation with a 0 determinant means it pushes everything to either a plane or a line or a point. But we're thinking of these in terms of the simultaneous equations of the planes. Right, we'll work this through. So with k is 12, with k is 12, do I want to do k is 12 first or k is 10 first? Hang on. With k is 10. All right. Let's do k is 10 first. Okay, what about trying to rule out these possibilities? Do we know whether they're parallel or not? Okay, so definitely not parallel. Definitely.
Sir, when we say then parallel. We're looking at the matrix itself, right?
Well, remember the matrix is representing three planes. The three planes are x plus 3y minus 2z equals 7. We are not thinking of them as transformations at the moment. We are thinking them as the equation of a plane. So there's three planes, aren't there? X plus 3y minus 2z equals 7. 2x minus 2y plus z equals...
Sir, I think you misunderstood my question. I was asking, like, when we say that one... what do we say? We say one row is a multiple of the other. We're talking about our matrix, right? 3 by 3.
Well, we're actually talking about our original equation, but we can see...
Yeah, I know. It's another form. Yeah.
Yeah.
Okay.
Yeah. Definitely not parallel. The Okay, so all you need to do now is find out with k is 10 and with k is 12 whether the equations are inconsistent or not. And that's the bit I haven't shown you how to do. So has anyone managed to get that? Because we can't use the inverse of the matrix to solve it. Okay, tell me. Yeah, well, tell me what you've done. Ah, you've spotted that. So if you spot that and understand what you're doing, then you can straight away see that in which case, do you say the first row plus the second row? So what Esther's noticed, I'll do this more formally so you don't get confused, but what Esther's noticed is the third row is the first row plus the second row. What that means is if you were to imagine trying to solve the first two simultaneously, you could end up generating a third one. 7 plus 3 is 10. So if k is 10, then all the equations are consistent. They agree with each other. And that means they will intersect at a sheaf. If k is not 10, then if you add them together, you get a pair of inconsistent equations. Now, we'll try and show that. So if you're not sure about that, we'll try and show it this way. So x plus 3y minus 2z equals 7. And I'm going to write them all out again because I think it'd just be easier to see. Right, we're going to eliminate one of the variables. I think the variable I want to eliminate is x. So I know we're not using matrix methods to solve these equations. That's because it has no inverse. We can use the reasoning Esther has just used, but if you're uncomfortable with that, how would we eliminate x? We would go 1 minus 2 gives you 5y minus z minus 3z.
2x. Yeah.
Oh, dear, oh dear. Is that right? So we have to do 2 times equation 1 minus equation 2 gives 8y. Yeah. Minus 4z minus 5z equals 11. Okay, and we're going to try and eliminate, we're going to do 1 and 3. So we're going to do 3 times 1 minus 3, which gives us 8y, good, minus 5z, good, equals 21 minus k. Okay, that makes sense? Okay, so if k doesn't equal 10, equations are inconsistent. Because you can't have them both true at once. If k is not 10, you can't have them both true at once. Yes. So what I'm showing you there is a general approach for doing it. Because there was a nice one that Esther spotted. If we started this and we just wrote equation 1 plus equation 2 gives us 3x plus y plus z equals minus z equals 10, then we can straight away go to the conclusion. Okay, but that's an artifact of them being so trivially easy to add to each other. So if k doesn't equal to n, the equations are inconsistent. If the equations are inconsistent, that means they can't all be true at once. So it's a prism. If k equals 10, well, we already know that they don't intersect at a point, but they are consistent. There's a sheaf. Okay. Yeah.
So we have x plus 3 minus 2z equals. So we have 1 and 2, and you can add them to get 3. And then that shows they're consistent. But does that show they're all consistent if 1 and 2 also have solutions as well?
No. So we wouldn't have ruled out, we're talking about the set of equations being consistent. So it's any two equations, any two of them are going to be consistent with each other unless they're parallel, aren't they? Yeah. So what that's trivial. Always the case unless they're parallel. We've ruled out the fact that they're parallel. If you hadn't ruled out the fact that they're parallel and you tried to do this, what would happen? Well, you would get them being inconsistent straight away. Okay. I don't think this is easy. You have to be very careful with it. I've started this exercise. I can tell you that question 1 is easy, is all I can tell you. That's as far as I've got. But that's probably more than you've got time for in the next 5 minutes. So work through it. So I'm going to just set you a task. I want you to finish the previous exercise. There was a homework which we talked about yesterday. If anyone still has any outstanding questions from that homework about the De Moivre's theorem in the exponential form, please ask again now. Get started on this now, and I'll put it on file right now that I want to finish exercise 2.1.
So
Yes.
I forgot to ask you yesterday about the homework. Can I ask you now?
About the what?
Homework.
Yeah,
or
sure, you can. Yeah. Let's get it. Okay, go for it.
So question 6. Yeah, I read your solutions and I kind of got confused.
So this is question 6, yeah?
Yes.
Okay. Are you able to tell me where it gets confusing for you? Or do I need to look at your work? I can look at your work, or you?
No, because I tried doing sine to the power of 3 and then cos to the power of 4, but I realized it didn't work. But then I looked at your solution, and I don't remember, but at some point I kind of lost what you've been doing.
Okay, well, so if you don't have work for me to look at, then what you want to do is look at what I've got. If you can see it on the screen, there it is. You can tell me where you lose it, or just I can talk it through from the start. Do you want me to talk it through from the start?
Can you please do that?
Okay, so we know it's one thing we've got to be very quick with, that when we see cos theta, we can write it as z plus 1 over z over 2. Yeah?
Yes.
Z is e to the I theta, so it's rather like the hyperbolic trig function. It's e to the x plus e to the minus x, except here it's e to the ix plus e to the minus ix over 2. You see the link with cosh?
Yes.
Okay, so we write that to the 4, and we do the same with sine, which is z minus 1 over z over 2i to the 3. Okay? I am then going to multiply it all out. Now, this might be where you've got confused, because I've noticed a clever way of multiplying it out. I could have used the binomial expansion to multiply that out to the power 4, and the binomial to multiply that out to the power of 3. But that feels, and then multiply them together, that's going to be a lot of work. So I've spotted a clever way of doing it, which is to use the difference of two squares to see that it's the same as z plus z to the minus 1 over 2 times z to the minus z minus z to the minus 1 to the 3 times z plus z to the minus 1 over 2.
Oh, I think yeah, that's where I lost you. I didn't get
okay. Do you see it now?
No, not really. Can you explain it?
Yeah. Okay. What about that?
I just don't see how you times z minus z to the power of -1 over 2i by z plus z to the -1
Right, okay.
over 2.
Sorry, do you understand what I've written on the board now?
Yes. Yes.
It's just the same as above, isn't it? Right?
Oh,
That's the
I
same as that,
see.
right?
Yes.
Okay. So instead of doing it as something cubed times something cubed, I'm going to do it as something times something cubed. So you happy with that?
Yes. Now I see. Okay.
Now what I've got now is I can use difference of two squares to multiply that out. So it's just
Yeah.
simplified the algebra enormously.
Oh my gosh. Yeah. It was an easy step. I just missed it
Okay.
out. Yeah.
No, it was.
Thank you,
That was the clever bit of the algebra. It would have been a horrible one to put as an exam question without a bit of help, because you can imagine how many students would have just gone and multiplied it all out and taken forever to do it. Okay.
So sorry.
Sorry, Belva. Yeah. So you missed the start of the lesson, didn't you? Do you want me to go through something?
But I don't actually know like how much I've missed.
Okay. So there's the
Oh,
note.
I think I've gone through all of them.
Do you understand all that? That's where I started.
Yeah.
Yeah.
I think so.
And
I was just wondering if there's a sheaf, why does it make the matrix singular?
well, because if you look at where I've started to try and solve the simultaneous equation, we'll use this as an example. If this has an inverse, right? If I can find the inverse of this matrix, then I'm going to find a value for x, a value for y, and a value for z, aren't I?
Yeah.
That means if the matrix has an inverse, I get a single point solution. If that had a matrix, I would get a single point as the solution. Right?
Why is it single point? Can
Well,
you not get a line?
No, because imagine this is a number. Let's get rid of the k. Just make k equal to number,
Yeah.
right? If I've got the inverse of this matrix, to find the answers, I'm multiplying that matrix by this column. I'm going to get a column with three numbers in it.
Yeah, so that would make a line.
No, a point. It would tell you that x was equal to something, y was equal to something, and z was equal to something.
Ah, right, yeah. Oh, I see.
So you would get a single point. So if it's singular, it's telling you you're not getting a single point. And we found out that might be because you get an infinite number of points, or it might be because you get no points at all.
But can we be asked to find a line?
Yes. So what you're asking is if they're a sheaf, could you be asked to find the equation of the line that they intersect at?
Yeah. So
Yes,
then
you
do
can
we
be,
have
and
to
you will
use
be. It's in the exercise.
Oh, okay.
Okay.
Yeah.
So that's what we'll be looking at tomorrow. Okay.
Okay. Thanks.
Bye bye. I've got to go.
Bye.
Bye.